morning, everyone. I hope you had a good afternoon yesterday. Our speaker this morning is Pascale Garaud, and she's joining us remotely from her home in California. And Olga Trichenko has kindly agreed to do the introduction. So I'll just handle the questions from this end after the talk, but Olga will be otherwise chairing the session. So over to you, Olga.
Thank you so much. It's my pleasure to introduce our plenary speaker this morning, Dr. Pascale Garaud. She's a professor in the Department of Applied Mathematics at the Baskin School of Engineering at the University of California in Santa Cruz. Professor Garaud obtained her PhD from Cambridge University in 2001 under the supervision of Professor Go, who was at the Institute of Astronomy, and Professor Rice, who was at the Department of Applied Mathematics and Theoretical Physics, which sounds like it was truly at the intersection of applied mathematics and astronomy. She stayed in Cambridge for postdoctoral studies funded by multiple fellowships before moving to UCSC in 2004. Now, her research focuses on fluid dynamics and magnetohydrodynamics applied to astrophysics and geophysics, involving a wide range of techniques from asymptotics to high performance computing. So I was told before doing this introduction that in astrophysics, it's common to make simpler models of very complicated fluid processes in stars rather than trying to model them with every possible detail, which could become intractable. Moreover, astrophysically realistic conditions are often beyond the parameters that are computationally accessible to direct simulation. So it's important to study the fundamental physics and look at asymptotic reductions, which is what Dr. Garaud does. In addition to her many publications, Dr. Garaud has also won several awards, including UCSC Excellence in Teaching Award, NSF Career Award, as well as becoming a fellow of the American Physical Society, and she currently holds multiple NSF grants. Dr. Garaud is an associate editor for geophysical and astrophysical fluid dynamics and on the editorial board of the Physical Review Fluids. Dr. Garaud is also involved in training the younger generation of astrophysicists and fluid dynamicists by being on the faculty of the GFD summer program, as well as the founding director of the Kavli summer program in astrophysics. Without much further ado, I now turn the mic over to Dr. Garaud for her talk on stellar fluid dynamics.
Thanks, Olga, for this broad introduction. Can everybody hear me properly? All good?
Yes.
Yes, okay, great. So thanks, Rebecca and the organizing committee for inviting me to speak today. And thanks to everybody who woke up early to come to my talk. So it was quite challenging to choose a topic that may be of interest to a broad audience of applied mathematicians such as yourselves, because my research is effectively quite applied to astrophysics in general. So I chose to present some work that's not as recent as what I'm currently doing, but is a good example of use of applied mathematical tools in the field of stellar fluid dynamics, a bit like Olga just described. So the first part of the talk is really meant as an introduction to stellar astrophysics and more specifically to the role of fluid dynamics in stars. And then I'll go into more detail of the fluid dynamics later. So as I'm sure most of you will recognize, this is the Milky Way. This is our own galaxy. And in this image, every dot of light is a star. And in fact, almost all visible light in the universe comes from stars. And in planetary systems, around stars like our sun is likely the host of life in the universe. So it makes understanding stars and their evolution quite a big subject of astrophysical research. But with only very, very few exceptions, one of which is the sun, each star is only a point source of light. And so that point source is the only information we have about it. And so for the longest time until, say, the beginning of last century, we knew very little about stars, and we didn't know what they were made of or what powered them. But that changed in the early 1900s with the birth of modern physics. So the development of atomic and particle physics, the development of quantum mechanics, and the birth of special and then general relativity. And with these tools, Cecilia Payne was the first to make the discovery that stars are actually made mostly of hydrogen in great parts, and to another great part of helium. And then all these other elements that we're familiar with on Earth only make a tiny, tiny fraction of the star's composition. And then around the same time, in 1920, Aston measured the masses of the hydrogen atom and the helium atom. And he found that the mass of one helium atom is ever so slightly smaller than the mass of 4 hydrogen atoms. And this led Eddington to realize that you could extract energy from fusing 4 hydrogens into 1 helium. And that energy is essentially given by Einstein's famous rest mass energy formula, E equals mc squared, where the mass in question is the difference between the mass of 4 hydrogens and heliums. And so basically stars shine because they fuse helium, as they fuse hydrogen into helium during their lifetimes. And it took another 20 or 25 years to figure out exactly how they do it, because it's actually quite difficult, and to work out the rates for the nuclear reactions. But eventually by the mid-1900s, scientists had figured that out. And so today, thanks to these early developments of stellar astrophysics, we have a pretty good understanding of stellar structure. And these are described by these equations. So basically the first and most important equation is hydrostatic equilibrium, which is a balance between the gravity, which pulls the star inwards, and pressure, pressure gradients, sorry, that pushes the fluid outwards. Then there's Newton's law of gravitation written here, which relates the gravity at some place in the star to the mass enclosed within a spherical shell. And then there's an equation of state, which relates the local pressure to the density, temperature, and composition of the star. So these are the structural equations. Then, of course, because of these very high pressures and densities at the center of the star, it's also very hot there. And that's where you can trigger these nuclear fusion reactions. And that keeps the star hot and high pressure in the center for billions of years. And so these next 2 equations here basically describe nuclear generation and transport of energy. So the first one describes how nuclear energy is generated at a rate epsilon inside the star and relates that to the stellar luminosity at a given spherical shell. And that nuclear generation rate is a function of the local density, temperature, and composition. And finally, there's a last equation, which is the equation of thermal equilibrium. And that one relates the local temperature gradient to the heat flux. So it tells you basically how heat is carried from the center of the star to the surface. And the formulation is different whether the energy is carried by photon conduction or whether it is carried by fluid convection. So in the sun, for example, the outer 2/3 of the sun in radius are convectively unstable, so heat is transported convectively, while the inner 2/3 are convectively stable and heat is transported by photon conduction. And so the function here takes a different form, whether you're in a radiative region or a convective region. So these are the equations of stellar structure. Now, I want to point out that the ones in black here, here, and here, these are very basic classical laws of physics, conservation laws, hydrostatic equilibrium, etc. And the devil in the detail really lies in these colored equations. The green ones for the equation of state, the nuclear reactions, and radiative transport depend on microphysics, so quantum mechanics, statistical mechanics, etc. Whereas the red one depends on turbulent transport by fluid flows. And so this is the first and probably the most important part of fluid dynamics in stars, is just convective transport. And the first model of heat transport by convective motion, as applied to stars, was proposed by Erika Vitense in the early 1950s. And so her work on stellar convection basically completed what is now known as the standard stellar model in astrophysics. So these are these equations. They, of course, have to be complemented by boundary conditions of the surface of the star. And these can be quite complicated. And then the input parameters for each star, we need to give the model its stellar mass. And we need to also assume a composition profile for the star, because here you can see there is no equation for composition. So with these input parameters, you can then predict, or you can then compute the pressure, density, temperature, and luminosity as a function of radius. And you also get out of the model the radius of the star. Now, not all of these are observable. And in fact, there are very few observable outputs of the model because we only see stars at point sources. And so very occasionally, you might be able to observe the stellar radius if you're lucky enough to have a stellar transit. But in general, the only two things you can observe really are the surface temperature and the surface luminosity. And this is why when astrophysicists compare models with observations, they almost always compare it in this form. So this is called a Hertzsprung-Russell diagram, and it shows proxies for the stellar luminosity on the y-axis and a proxy for stellar temperature on the x-axis. And each dot in this diagram here is an actual star belonging to various open clusters in our galaxy. And their properties were measured using the recent Gaia mission. And different colors in this diagram here represent not the color of the star, but it represents their ages. So the blue dots are very young stars, whereas the red dots are much older stars like the sun. So the solid red line here is basically what you would get from solving the equations of stellar structure that I showed you earlier, using an assumption that the composition is homogeneous with about 3/4 hydrogen and 1/4 helium, and just traces of heavy elements. And the mass of the star is basically the parameter along this line in the diagram. So low mass stars are here and high mass stars are here. And you see essentially that the model provides a really good fit to the data for young stars, for the blue stars, but not so much for the red ones up here. And that's effectively because the blue star, the young stars, are indeed very close to being chemically homogeneous. But the process of nuclear burning, which converts hydrogen into helium, effectively creates inhomogeneities in the composition. And in fact, eventually the star runs out of hydrogen in the core. And when that happens, the stars move off this line and become very bright and very red. And they're called red giants. And so the process by which the stars leave this line, which is called the main sequence, and become red giants is a process that can only be studied if you drop this assumption of steady state and input composition, and you actually solve for the evolution of the composition of the star instead. And that's where things become tricky, and that's where fluid dynamics start to really matter. So the composition of the star evolves, like I said, because of nuclear reactions, transforming hydrogen into helium mostly. And these are well understood. So these are these black terms here. And they are local in a particular region of the star. But the problem is that this evolution equation also depends on advection by fluid flows, which is non-local. So this transports various chemical elements from one region of the star to another. And in particular, these fluid flows can take hydrogen from the surface and bring it into the core. And that brings fuel to burn in the core, and that prolongs the star life on the main sequence. And that affects stellar evolution very substantially. So the point really is that you can't do a good job of understanding how stars evolve without understanding stellar fluid dynamics and its impact on the star's composition. So what do we really know about stellar fluid dynamics? Well, recently there's been progress using helioastroseismology, which helps us measure fluid flows inside stars to some extent. And so we know from that in many ways stars are very similar to, or stellar fluid dynamics is very similar to the dynamics of the Earth's atmosphere and oceans. And in particular, in both stars and in the Earth, there are regions that are convectively stable and regions that are convectively unstable. And we also know that rotation is important in governing the dynamics of fluid flows, both on Earth and in stars, and stratification is important in controlling these flows. More specifically, we know from observations that stars and the Earth both have large-scale meridional flows. These are these large-scale circulation cells. So here is basically a cartoon picture of the Earth flows in the atmosphere. And you can see these large-scale circulation cells in the atmosphere transporting fluid from the equator to the pole and vice versa. And similarly, similar flows exist in the solar interior below the surface, and these have been inferred from helioseismology. And so these large-scale meridional cells transport both heat and chemical elements between the equator and the poles. And at the same time, they also transport angular momentum, and that accelerates fluid in the azimuthal direction. So it creates these large-scale azimuthal jets that we know on Earth. So the westerlies at high latitude and the easterlies at low latitude that we ride on an airplane to go faster, basically. And for comparison, here's a figure of azimuthal flows in the sun. So this is just a picture of the solar rotation rate in nanohertz as a function of radius and latitude. And so you can see that the equatorial regions are rotating rapidly. So there's a large scale fast jet, whereas the polar regions are rotating slowly. So there's a large scale slow jet in there. So there's really a lot of similarities between the two. And to some extent, it shouldn't really be coming as a surprise that they are similar, because at heart, they're governed by the same equations of fluid dynamics. So I've written them here in what's called the Boussinesque formalism. That's applicable to model the Earth fluids in atmosphere and the ocean, as well as stellar fluids deep inside the star. So you have a momentum equation, F equals ma, with the forces here, and the mass times acceleration here. There's a statement of incompressibility, an equation of state, an evolution equation for temperature, and an evolution equation for composition. Now, the compositional equation is just a really standard advection diffusion equation. And then the equation for temperature, on the other hand, contains this extra term. And that accounts for the heating and cooling that comes from a parcel of fluid compressing or expanding as it moves up and down in the star. So it depends on the vertical velocity of the fluid, as well as what's called the adiabatic temperature gradient. And so, given that you have similar processes and similar equations, I would argue that the only real difference between geophysical and stellar fluid dynamics are listed here. Stars do not have topography, but topography is really key to the weather and the climate on Earth. The physical parameters in stars, of course, are really different from physical parameters on Earth. Gravity is different, the size is different, and the properties of the fluid are different. And then in stars, magnetic fields are really important, but on Earth, they're typically not important in the ocean and atmosphere. And so if you ignore the magnetic fields for now, and while you might think it's not a good idea for a star, most stellar astrophysicists do ignore magnetic field to a first approximation. And if you also ignore topography, because there's no topography in stars, then really you might start thinking that stars are actually simpler than the Earth, because they're the same fluid dynamics equation, just different physical parameters and no topography. And so then you might even wonder whether we could use some of the really sophisticated climate and weather models that we have for Earth modeling, such as this is a picture made by the E3SM model created by the Department of Energy. So we could think maybe of using some of these sophisticated models to study the dynamics of stars instead of the atmosphere and the ocean. You just have to remove the topography, basically. And unfortunately, this is where things are not very simple, because first, on Earth and in stars, it's not possible to run numerical simulations that resolve at the same time all the length scales and time scales of the system. And it's especially true for stars, where the overall evolution timescale is billions of years, which is much, much longer than any fluid timescale, which might be taking place on timescales as fast as, a day or even an hour. So the point, though, is that these models of the Earth's ocean and atmosphere very heavily rely on parameterizations to describe the effect of really small-scale turbulence on the transport of heat, chemical, and momentum. And for Earth, these parameterizations are tested really extensively against laboratory experiments, in situ measurements, and high resolution simulations on much smaller scale than the whole Earth. So these parameterizations are reasonably reliable, and that's why these weather models are, at the end of the day, actually pretty good. But stars and stellar fluids have very different physical properties. And so there's no reason to believe that the same parameterization that were developed for Earth models also apply in stars. And that's in fact the main message of this talk, is ultimately that these subgrid scale turbulence models for Earth do not apply at all to stars. So the goal here will be to create new subgrid scale turbulence models for stars that can be used in global scale simulations and ultimately also in stellar evolution models. And if we want these subgrid scale parameterizations for stars to be reliable, then we also need to do experiments. And in stars, this becomes very difficult because obviously in situ experimentation is impossible. And more importantly, the physical properties of the fluid that stars are made of, which is basically plasma, are not ones that can be achieved in laboratory experiments on Earth. So the only remaining option is to run direct numerical simulations. And this involves solving the full set of equations I showed you earlier, resolving dynamics at all scales, both the large and the small. And to do that, we're forced to focus on very small domain simulations, tiny, tiny regions of a star, where we can indeed resolve all the scales. And so in everything that followed, when I'm talking about models, I'm going to talk about small domain models as a tool for experimentation in stellar fluid dynamics. So to recap this part one, the goal here is going to be to better understand stellar fluid dynamics and its role in transporting heat, composition, and momentum in stars in a way that we can then better understand stellar evolution. And to do that, the missing piece at this point in time is really a reliable set of subgrid scale parameterization that can be obtained in principle from these small domain simulations. And so that's the goal here. Okay, so that was basically a very general introduction to give you an idea of the really big picture. And now I'm going to go into more detail into why turbulence in stars is so different from turbulence in geophysical fluids. And in order to really understand why, I'm going to need to introduce this important fluid property called the Prandtl number. So in studies of fluid dynamics, and I'm sure in most studies in applied mathematics, we work typically with non-dimensional equations because that reduces the size of parameter space that needs to be explored. So the first task is to take these governing equations and non-dimensionalize them. These are the same as I showed you before, minus the rotation and the magnetic fields. And the only thing I've done here is substitute the equation of state into the density so that I don't have to follow that around. Also reminding ourselves that basically we are working these tiny boxes in a star. I can assume that gravity is constant and some of the mean physical properties like the diffusivities, the viscosity, these are all constant on average in that box. And then for convenience, we almost always split the temperature as the sum of a background that might be provided by these large-scale models and set the stratification. And then the perturbations, and it's the evolution of these fluctuations that we are studying in these turbulent DNS. Okay, so with that substitution of background plus fluctuation, we now have a set of equations for these new independent variables that are the pressure fluctuations, temperature fluctuations, composition fluctuation, and the velocity field. And then with that, we can define a new system of units where the unit velocity might be the characteristic or RMS velocity of the fluids. The new length scale will be the characteristic length scale of the turbulent eddies. And then units for temperature and composition are basically the typical size of these quantities that would be generated as eddies stir up the background stratification. And with that, in this new system of units, the equations look like this. And there are several standard non-dimensional parameters that come up in front of the buoyancy term here, and in front of the diffusion terms here, here, and here. Now, the most important of these parameters that you might have heard of if you do fluid dynamics is the Reynolds number. And the Reynolds number is essentially an estimate of the size of the ratio of the advection terms in red to the diffusion terms in blue. And then you have a similar term in the temperature equation, the Pascale number, which is also a measure of the size of the advection term in comparison with the diffusion terms. And of course, you could do the same for the composition equation as well. Now, one of the key results in turbulence theory, which dates back almost 100 years ago, but was formalized really by Kolmogorov, is that turbulence only exists if in the momentum equation, the nonlinear terms largely dominate over the diffusion terms. So in other words, if this Reynolds number here is much, much larger than 1. And then similarly, this turbulence advex temperature, or primarily advex temperature only if this Pascale number is much, much larger than 1. And it's important for what follows that both of these conditions depend on the flow properties, so how fast it is and how large the eddies are, as well as the fluid properties, the viscosity and the thermal diffusivity. But on the other hand, if you take the ratio of these two numbers, the ratio of the Pascale to the Reynolds, that is this quantity I refer to as the Prandtl number. In this ratio, the flow properties disappear, cancel out, and all you're left with are fluid properties. So the ratio of the kinematic viscosity to the thermal diffusivity. And so the Prandtl number is intrinsic to a given fluid. For a given fluid, the Prandtl number is known. And so fluid on Earth, like air and water, have typically a Prandtl number that's of order unity. And that means that if the conditions for turbulence are realized, as in the Reynolds number is very large, because the Pascale number is Prandtl times Reynolds, and Prandtl is order 1, then the Pascale number is also very large. And that tells you that the evolution of the temperature field in this turbulent flow is also dominated by advection. So in geophysical flow, turbulence always advects the temperature field. On stars, on the other hand, and that's what makes them different, the Prandtl number is extremely small. We're talking about numbers of order 10 to the minus 8 to 10 to the minus 5. So there's always a range of scales for which we can have a very large Reynolds number still, but at the same time, a very small Pascale number, because if the Prandtl number is extremely small, it's possible to have this. And in that case, there's always a range of scale where the turbulence is thermally diffusive, meaning that advection is then negligible. And that's really unique to stars. It can never happen in these geophysical fluids. And that's important because now it should help you see why we cannot export geophysically derived subgrid scale model to model turbulence in stars. The subgrid scale parameterizations in geophysical fluids were created assuming that the turbulence advects temperature, whereas the subgrid scale parameterizations that would be relevant for stellar fluids must necessarily involve a thermally diffusive dynamics, right? So low Pascale number dynamics. And these are very, very different. And in order really to see why that's the case, I want to introduce now these low Pascale number equations. So low Pascale number turbulence, diffusive turbulence, can be studied using a reduced equation that was derived by François Linière in 1999. And the derivation effectively goes as follows. So if you recall the non-dimensional temperature equation, which is written here, and you now look in the limit where the Pascale number is asymptotically small, then a natural way to proceed would be to try and do an asymptotic analysis and posit that each of the dependent variable can be written as an asymptotic series in the Pascale number. You then take that series and plug it back into the governing equation here. And this is what you get. And I've color-coded terms that are of the same order in Pascale. So at the lowest order here, we have a term in 1 over Pascale, and then at the next order, we have a term order 1. and everything is higher order. And so you can immediately see that this lower order term is unmatched. And that tells you that at the lowest order, the temperature fluctuations must be zero. And that's very important because it has a fundamental consequence. You can call it the zeroth law of low Peclet turbulence if you want, is that the temperature fluctuations being zero at the lowest order means that the temperature stratification remains unaffected by fluid flows in stars at lowest order. So the temperature profile must remain very close to whatever was imposed in the first place. And in particular, this says that there's no possibility for thermal layering in stars, at least not small scale. And that's really, really different from what happens in the Earth's oceans and lakes, where you often observe spontaneous thermal layering. This is an illustration of that. So these are measurements taken from the Arctic Ocean by Timmermans et al., showing a temperature profile. And you can see that on the small scales, here, the temperature profile takes the form of a staircase. So these are layers that have uniform temperatures. And this kind of profile is indeed created by turbulent mixing of temperature on the small scales. And the fact that it's not smooth is really a consequence of the fact that advection dominates in geophysical flows. And in stars, you would never, ever see this as long as the Peclet number is small. So that's one first fundamental difference. Now, at the next order in this expansion, you have a balance between these terms in blue here. On the left, the advection terms, and on the right, the diffusion of the first order temperature fluctuations. And knowing that the T0 terms are now zero, you're left with something really simple here. And remembering now that T tilde is now written as Peclet times T1, you can substitute that back in here and obtain that the vertical velocity UZ is simply 1 over Peclet times the Laplacian of the temperature fluctuations. And so comparing this with the original non-dimensional equation, this with this, you can see that the main thing that happened is that the nonlinear advection terms here just dropped out of the equation. And that's really not surprising because this low Peclet number limit is the limit where advection is negligible. So it's not surprised these terms dropped out. But in practice and moving forward, this means that the vertical velocity field and the temperature field are effectively tied to one another at every point in time and space by this equation. And there are many interesting consequences of that reduced equation. But in my opinion, the most interesting and simple one comes from writing it dimensionally. So this is what it looks like when we put back the dimensions, right? So we have a balance between the vertical advection of the temperature stratification and the diffusion of the temperature fluctuations. Now you can solve this equation for T tilde and write this as this constant times the inverse Laplacian of the vertical velocity. And this shows that for low Peclet number fluid dynamics, these parameters, the stratification and the thermal diffusivity, never appear separately. They must always appear together as this parameter group, as this ratio. And that immediately tells you that at low Peclet number, if you want to create a subgrid scale model, it has to depend on this ratio rather than stratification and thermal diffusivity separately. So that's a huge hint as to what form a subgrid scale parametrization ought to take. Now, you can also go further and substitute, this equation for the temperature fluctuations back into the momentum equation over here. And now you can see that the buoyancy term is replaced by this inverse Laplacian of u times this constant. And with that substitution, you can now completely ignore the temperature equation and have a closed system that only involves the evolution of the velocity field. So that's both easier to solve numerically and has some interesting consequences mathematically I'll discuss in a minute. But we now see that also the relevant parameter group is actually alpha g times this ratio. And alpha G times the stratification has the dimension of a frequency squared, and that frequency is called the buoyancy frequency N. But effectively, the larger the buoyancy frequency, again, the stronger the stratification. So in what follows, it's really this ratio, the buoyancy frequency squared divided by the thermal diffusivity, that's going to matter. Okay, so enough of the mathematics for now. Let's see whether this asymptotic limit or these low Peclet number equations are actually valid, and for which values of the Peclet number are they indeed valid. So we're going to consider a simple toy model in which we look at a stratified fluid, so which is denser at the bottom than it is at the top, and impose a body force in the horizontal direction that's going to drive a sinusoidal shear flow. Now, shear, if you don't know the terminology, is basically the gradient of velocity in the direction perpendicular to the flow. So here we have flow in the horizontal direction, and so we have shear in the vertical direction. And it's very well known that shear can drive instabilities and small-scale turbulence, as long as the stratification is not too strong. So the equations governing that particular model are written here. So these are non-dimensionalized again, in the same way as before. You see the buoyancy parameter that appears here is called the Richardson number. It's written in this form. And if you then play the same game, take this equation here, solve for t, substitute into here, you get that the low Peclet number version of this equation takes this form non-dimensionally. And now you can see that the relevant stratification parameter is the product of this Richardson number and this Peclet number. And again, it shouldn't be surprising because the only thing we really care about are things that depend on the ratio of n squared and kappa t. So it was inevitable that that the product of Richardson and Peclet should be the correct stratification parameter. So we then ran three-dimensional simulations of this model system and measured, for example, the RMS velocity of the flow as a function of this Richardson-Peclet product. Now, the result for the full equations are shown in green, blue, and yellow at different Peclet numbers. And the result for the low Peclet number equations are shown in purple. And you can see that the measured RMS velocity for the low Peclet number equations is an almost perfect match to those for the case of a low Peclet number simulation in green, and it's a pretty good match also for the case of a Peclet number equals 1 simulation in blue. On the other hand, of course, they are not a good approximation for the case of a Peclet number 10 simulation, but that's not surprising because that's not in the regime of validity of these asymptotically low Peclet number expansion. So these results really validate the use of these reduced low Peclet number equations when the Peclet number is smaller than 1. So this is the end of the second part of the talk. And to summarize, basically, in stars, the Prandtl number is asymptotically low. And there's always a range of scales for which you both have turbulence, a high Reynolds number, but that turbulence is thermally diffusive. So you have a low Peclet number. And that's unique to stellar fluid dynamics. Now, that turbulence has several properties. It cannot modify the background temperature stratification. And it can only depend on this dimensional parameter group, the stratification over the thermal diffusivity. So subgrid scale model, for instance, can only know about this parameter group and not n squared or kappa t separately. And finally, there is an interesting equation that can be derived in which you can eliminate temperature and get a closed system for just a velocity field. So we have a reduced model with fewer dependent variables. And that has been validated. Okay, so now in the final part of the talk, I'm now going to go into a little bit more detail about a particular topic of research that I'm interested in, namely that of shear instabilities in stars. And I'm going to use some of the results I just mentioned, namely the insight gained from dimensional analysis and the dimensional reduction that comes with low Peclet turbulence, to try and understand properties of shear-driven turbulence in stars. So I just want to remind you first that there's at least one star that we know of that has a lot of shear, and I showed you this picture earlier. So this is again the rotation rate of the sun as a function of latitude and radius, and we can see substantial horizontal shear in the outer layers in the convection zone, as well as substantial radial shear here just below the base of the convection zone. So I'm going to ignore the horizontal shear for now and just focus on the radial shear. And the questions we want to answer is or basically that a subgrid model should try and capture is whether this shear is indeed unstable or not, and whether we can model the turbulent transport that it causes if it turns out to be unstable. So to answer the first question, namely whether the shear is unstable, we could first look in the existing literature. So there's these really seminal papers by Miles and Howard, who derived a formal instability criterion for vertical shear instabilities in stratified fluids in the non-dissipative limit. Okay, and the instability criterion goes as follows. It states that the gradient Richardson number, which is the ratio of this buoyancy frequency squared to the shearing rate squared, that number has to be smaller than a quarter somewhere in a fluid for instability. And physically speaking, it just means that the shear has to be strong enough to overcome the stable stratification for the instability to develop. So it sort of physically makes sense. But in stars, actually, if you compute this gradient Richardson number, you'll find that it's always extremely large. So in the solar tachocline here, for instance, if you compute it, it's of order of 1,000. So that would naively suggest that, or I mean, it would state that the shear cannot be unstable to these non-dissipative shear instabilities. Now, of course, that doesn't mean that shear instabilities are ruled out in stars. It just means that non-dissipative instabilities are ruled out in stars. But as we saw, in low Prandtl number stellar fluids, thermal diffusion is often very important. So what we must ask instead is whether there might be thermally dissipative instabilities instead. Now, and one strong hint as to what's happening is that, you know, this from dimensional analysis, this Miles-Howard criterion that I showed you earlier cannot be of the correct form for low Peclet fluid, because if it was, it would depend on n squared over kappa t. It would know about thermal diffusion. So we cannot use this to model thermally diffusive instabilities in stars. We have to find another criterion that knows about thermal diffusivity naturally. And that begs the question really of what is the correct stability criterion for diffusive shear instabilities? And here, to my knowledge, there is no general formal equivalent to the Miles-Howard theorem for thermally diffusive shear instabilities. And by this, I mean that we tried to find one, but we failed. Now, on the other hand, you can use dimensional analysis to try and get an idea of what such a criterion would look like if it existed. So remember that in low Peclet number fluids, the only parameter that you're allowed to use to capture the effect of stratification is this one, n squared over kappa t. In addition, you have information about the shearing rate, the flow velocity, the length scale, as well as viscosity. So these are the dimensional parameters you're allowed to use to create a criterion. And so from that, you can see that there's only really two meaningful non-dimensional criteria that one can form from this combination of parameters. The first one here is basically stating that the product of the Richardson number and the Peclet number has to be smaller than something of order 1 for instability. And in fact, that criterion has been proposed many times over the years, and the first time I've seen it was by Townsend in 1958. The second way of forming a non-dimensional criterion from these numbers is this one here, and it effectively states that it's the product of the Richardson number and the Prandtl number that has to be smaller than something of order unity. And that criterion was first proposed by Zahn in 1974. So again, this is just from dimensional analysis. There's no mathematical modeling behind that. But we can use DNS again to test whether these criteria are meaningful at all. So this is the same model as before. And in this case, we'll just focus on the low Peclet number equations written here, since we're wanting to probe that limit. And I just want to point out here that because now we're looking at stability around a steady state, laminar flow, we're going to use the laminar flow velocity as the unit velocity of the system. But everything else is essentially the same. So if we use a triply periodic domain for the fluctuations, we can project these governing equations here onto a set of ordinary differential equations and get an infinite system of coupled ODEs in the usual way. Then you can study the linear stability of these ODEs to perturbations using tools of, say, dynamical systems theory. And this figure here shows the resulting stability diagram in the space of Reynolds number versus stratification, Richardson-Peclet. And the region to the top left corner here is linearly unstable to perturbations to the laminar flow. And to some extent, it's not surprising. It's just stating that for the system to be linearly unstable, you need the Reynolds number to be sufficiently large, so very little viscosity, and you need the stratification to be sufficiently small. But what's interesting from a quantitative perspective is that at high enough Reynolds number, this line here asymptotes to a vertical line that says that the criterion for instability is Richardson-Peclet equals 1/4. So that's really reminiscent of one of the two that I just showed you, which is the one that was proposed by Townsend. But again, using tools from dynamical systems theory, you can also ask the more interesting question of whether some regions of parameter space might be Lyapunov stable instead. And if you use energy as the Lyapunov functional, that's referred to as energy stability in fluid dynamics. So essentially the question here is a little bit different. It asks whether there are regions of parameter space in which the energy of a fluctuation and the evolution of that energy is shown here. So are there regions of parameter space where the energy of that perturbation always decays with time? And to identify that, you just need to identify regions of parameter space where the right-hand side of this equation is always negative. And one of the standard approaches to do that is to use Euler-Lagrange constrained optimization techniques to find the maximum of that right-hand side, and then simply require that this maximum be smaller than 0, because if that's the case, you have indeed guaranteed that the right-hand side should be negative. And this was first done for this particular stratified shear instability problem by Tobias Bischoff and Basile Gallet for flows with constant shearing rates. And in that case, the nice thing is the calculation can be done completely analytically. And they demonstrated that a sufficient criterion for energy stability is that the product of the Richardson and the Prandtl number should be greater than 1/4. And now that's really reminiscent of the second criterion I showed you, the one that was originally proposed by Zahn. And I want to add that a key element of their derivation was that it leverages on the structure of the low Peclet number equations, and you wouldn't be able to do a similar derivation using the full equations instead. So here, the asymptotic reduction of the equations before doing this Lyapunov stability analysis was really useful. So this was for constant shear. And for the sinusoidal shear flow I showed you earlier, the energy stability analysis cannot be done analytically, but the stability region can still be computed numerically. And it's shown here in red. So everything to the right and bottom of that red curve is not energy stable or Lyapunov stable. So all perturbations must decay. And it's interesting to see that the slope of that line is indeed the one given by Richardson-Prandtl number is equal to a constant of order unity. So consistent again with Zahn's proposal for the criterion. So both sort of proposals that we had earlier from dimensional analysis are actually relevant, but for different ideas. And then finally note that there's a large region of parameter space in the middle here, where finite amplitude instabilities are possible. And so in follow-up studies, we actually looked for these finite amplitude solutions, continuing linearly unstable solutions into the linearly stable region of parameter space. And each of these unstable solutions is shown as a red cross here in this diagram. And eventually, when the stratification becomes sufficiently large, the turbulent solution disappears. And what's interesting is so this would be the actual stability limit for this system. And this actual stability limit now takes the form Richardson-Prandtl is equal to 0.007. So that has the same functional dependence as energy stability, but with a different constant on the right-hand side. And interestingly, the same stability threshold was found for sinusoidal shear flow and for linear shear flows. So that's now a really robust result. And then finally, in terms of addressing the second question, and I promise I'll be really quick, which was that of parametrizing turbulent transport by this low Pecklin number stratified turbulence. Well, we ran a number of DNS to do that. From analyzing these DNS, we found that the turbulent effect could be modeled as an eddy diffusivity, which is not really surprising. But what's interesting is the eddy diffusivity turned out to be the same for momentum and composition. And so with that, only one model is needed for both. And then finally, using a combination of dynamic analysis and some physical motivation, we were able to propose the following model for the turbulent eddy diffusivity as a function of these relevant parameter groups, Richardson-Peckley and Richardson-Prandtl. And here's a figure showing a scaled version of that turbulent diffusivity as a function of Richardson-Prandtl. The solid lines are the model, and the symbols are the data with colors corresponding, and different lines correspond to different Reynolds numbers. And you can see that for a given color, the data falls on that line really well. And there was really only one parameter fitted to the data, which was this ratio here. And so I think we have now a decent parameterization for turbulent transport by stratified shear instabilities in stars. Okay, I'm going to skip this. I can come back to it if somebody's interested. So I just want to finish by saying that we focused here on a really simple example, which was the stratified shear instability problem. There are many other different types of instabilities in stars, some of which we have studied more recently, and some of which, of course, still need to be studied. But essentially, the steps and tools that I discussed today will be the same for studying these other instabilities. And of course, so far, mostly rotation and magnetic fields have been ignored, but eventually they will need to be taken into account as well. So the take-home messages here are basically fluid dynamics is really the next frontier in stellar evolution. We need to understand it if we want to better model stars. Small-scale turbulence in stars is really different from small-scale turbulence in geophysical flows. And it all boils down to the fact that the Prandtl number is much smaller than the one in stars. And then finally, I showed you through this one example how some standard tools of applied math can be used to study the small-scale turbulence and produce subgrid scale models that are relevant for mixing of chemical elements and momentum in stars. So thank you very much for your attention.
Thank you very much for your great talk. I learned quite a bit of very interesting dimensional analysis. I guess I now open the floor to questions, and hopefully Rebecca can help me with in-person questions as well.
Yes, I'm here to help.
Thanks.
I don't see any in the chat this moment. Are there any in the room?
Is Morris Flynn has a question?
Okay, we'll take that one first, and then there's one in the room.
Good morning, Pascale. Can you hear me okay?
Yeah.
Fascinating talk. Thank you very much. I wanted to ask specifically about part 1 and part 2 of the take-home messages.
Yeah.
You had said at the outset that our sun, the inner 2/3 of it, I think, is dominated not by convection, but rather by conduction. And so in terms of fluid mechanics being this kind of next frontier, if you had a star that was just a little bit smaller, would that consideration, actually fall away? Would it be the case that instead you could just do a purely conductive model of, say, heat transfer, and that would be good enough.
I realize I must have caused some confusion here. So the convection that I talked about in here, that is actually what you can see in this picture of the sun. This is this outer convection, right? That's a large scale fluid flow process that's not actually affected by any of what I talked about today. And so the models that were proposed a long time ago by Eric Vitense are still applicable for that. And so indeed, if you had a smaller star with a larger convection zone, her model would still apply. And what I talked about for these small scale processes would not be relevant. On the other hand, it's inside the stably stratified region that you have lots of other instabilities that take place, like stratified shear instabilities, rotational instabilities, buoyancy-driven instabilities that are not of the convective type. Mm-hmm. These are the instabilities that are typically small scale because of the stratification. And these are the instabilities for which everything I talked about is valid. Does that make more sense? So in some sense, what I said is going to be true for everything to do with the dynamics in the stably stratified regions of star.
Oh, okay. Yes. Okay. I got that.
Because when I talk convectively stable and unstable, I'm really talking about convection, which is a process by which the density is unstable. You can also have instabilities and fluid advection in a stably stratified region where convection is not excited.
Right. Okay. Yeah. Okay. Can I ask a second question then?
It would be nice if we could take the question from the floor here.
Okay. Sure. Okay. Fair enough. Thank you.
Yeah. So I was. Yeah. Really fun. So I just had sort of a question, specific equation. So in part 2. You're taking like an inverse Laplacian at one point, and it didn't seem to apply to the collection of terms involving temperature. It just applied to the UZ. I was just wondering if we were assuming that those other terms were constant in space.
I'm not sure I heard the whole question. Is there somebody who could repeat it? Is it something to do with this this term, the inverse Laplacian, right?
Yeah, just I might have misread, but it just seemed like it didn't apply to the other collection of terms in front of the UZ. So I was just wondering the DT, DZ, and it was maybe the following slide.
Oh, I see. So in here,
yeah,
right? These are assumed to be locally constant. And this term here is the one that varies sufficiently rapidly that we would actually care about this, right? This is almost constant on the scales that we're worried about.
Okay, yeah, I figured that had to be true. Thanks for answering.
Okay, quickly back to Morris, and then I think that's our last question.
Okay, super. I'll try to be brief. Pascale, I'll ask a question on behalf of Bruce Sutherland, who I don't think is here with us this morning. So point very well taken about the differences between the stellar fluid dynamics and GFD. What was interesting to me is that actually this exact equation that you're highlighting here, so when you say dimensionally, this is blah, blah, blah. If I understand this correctly, what you're doing is proposing a balance between vertical advection and diffusion. And I don't mean to get too highfalutin or too specific here, but is this not essentially the same balance that Walter Munk proposed in Abyssal Recipes when he talked about the evolution of stratification in the oceans?
Oh, that's quite likely. Yeah, because this is going to be valid whenever you have a very slow flows.
Okay.
Okay. Now, the key is that in stars, this is also valid for turbulent flows that happen to be low Peclet. In the ocean, you can only get this for extremely slow non-turbulent flows, but these abyssal overturning are very slow flows, and so this equation could also be valid.
Right, okay.
Yeah.
Okay.
So the important part for stars is that this even happens in turbulent flows.
Right. Okay. Okay. Thank you so much.
Thank you very, very much, Pascale. That was a wonderful talk.
Yeah, I don't know if you can see me, but thank you very much for everybody who stuck all the way to the end. Okay, have a good coffee break, everybody.
Yes, and I assume if people have further questions, they could contact you by email?
Yeah, of course, of course.
Super. Okay, thank you very much.
Okay, bye.